Welcome to the WEB.BM numerical example with channel routing. In this example, we are going to be solving the model using daily time steps on a system where the total travel time from the most upstream to the most downstream point is more than 1 day. We have a simple system with one reservoir and its inflow, one additional inflow from a tributary downstream, several river reaches through which we have to route the flows, and a downstream diversion from node 8, which is located more than 1 day of travel time from the reservoir. There's also routing through the city of Red Deer, which is one of the major cities in the province of Alberta in Canada. There are two modeling scenarios here. The first one, where reservoir releases are demand-driven on a daily basis for a system with travel time greater than 1 day. The second example deals with minimizing flood damage for flood that happened in June of 2013. The modeling objectives for the first scenario are to maintain minimum flow of 16 cubic meters per second throughout all river reaches, and also to provide demands at node 8, which are given as 15 cubic meters per second for all days except for the 6th of May, when these demands are increased to 100 cubic meters per second. In the second scenario, the objective is going to be to keep flow through the city of Red Deer at no more than 950 cubic meters per second. What happens if you try to use this single time step solution framework, which is common to most river basin models, and you try to allocate water to a downstream water use with a daily time step, although the travel time is longer than 1 day? A common misconception is that all you need to do is you need to use channel routing and it'll take care of everything. However, this is not true. The single time step solution mode with routing is not going to deliver a sensible solution here, because if you look at the solution in this particular matrix, we see that 16 cubic meters per second was maintained at the most downstream channel C on the 4th of May, then on the 5th of May, but on the 6th of May all of this water was diverted. Since the diversion to D1 has a higher priority, there was a large release from the reservoir of 354 cubic meters per second, and yet very little of it reached the downstream demand at D1. The reason being, it takes much longer for water to reach the downstream demand. And if you see what happens to the peak flow here, from 354, it was reduced to 188 in the next channel during the next day, and then it was reduced to 127 in the subsequent channel, downstream channel, for the following day. Finally, on the 8th of May, we can see that in channel C we had a flow of 107.088, and that was more than enough to divert into the demand block. However, at this point we don't need more than 15. We needed 100 to be diverted on the 6th of May. This clearly shows that we should have made this release 2 days earlier. Even the release is not correct, because we are showing a flow of 107 while we only need 100. So the trick here is to provide both proper timing of the release and the amount of the release that will satisfy the demand after all the attenuation processes have been taken care of along the reaches that require traveling between the reservoir and the demand node. One more thing, why did we release only 354? The reason is that we have this outflow versus elevation curve. If you can look at the starting level of 943.6 meters elevation and the ending level of 941.438, you can calculate the average elevation and read from this graph the average outflow capacity corresponding to this elevation, and that will be about 354. The travel time is the restricting factor, which requires proper timing of the releases. This issue, by the way, is well known. It has been published in the past, and if you want to see a numerical example that can easily be replicated in a spreadsheet, you can refer to this publication. That was published in 2008. A proper account for channel routing requires therefore both proper timing and proper amount, and the purpose of the model is to determine both the proper timing of the release and proper amount to be released. We also know that some of the releases are going to have to be required to fill the channel storage in order to allow the increase of flows through the channel. This is part of the river mechanics that has to be addressed properly by the model. How is it done? The model uses the SAR channel routing scheme, which starts from classical water balance equation for any channel, which you will find in any routing method. After a few transformations, this starting equation is converted into this equation. You will notice the term TS, which represents travel time. The travel time along the river edge is a function of flow. It is shown graphically here. It can be defined by knowing the average velocity of the stream that corresponds to a particular flow in the river edge. For very high flows, it is determined by observing the movement of the peak flow from the upstream end of the reach to the downstream end of the reach. For moderate flows, it is typically determined from the measurements, since every flow measurement includes the average velocity in the stream. This equation has the same form as the well-known Muskingum equation, where the term multiplying the inflow from the previous time step is a routing coefficient C1, and then you have the other terms representing routing coefficients C2 and C3. The same condition for Muskingum and other routing methods, that the sum of all three coefficients is equal to 1, is also maintained here. But the good thing about this is that we can go through the entire year by not having to recalibrate the model. The model calibrates its routing coefficients automatically based on the flows which are being allocated in the channel, and the flows are allocated by the optimizer. So there is an iterative scheme built into the model that takes care of the convergence. The solution for this particular time step is presented here. You will see that the model decides to release 300 cubic meters per second on the 4th of May in order to satisfy this demand of 100 cubic meters per second for the diversion and to maintain 16 cubic meters per second minimum maintenance flow at the end of the reach. So the total requirement is 116. This, of course, is met by a release which was made 2 days earlier. And there is a little bit of a contribution from the tributary. So reservoir release of 300 is increased slightly by the contribution from the downstream tributary, and then the combined amount is routed through the two downstream channels to give the entry of 118.3 to the most downstream channel, which at the end of the channel becomes 116. 116, by the way, is a total requirement. You can see how routing was conducted through all three sequential channels. The release from the reservoir does show that we do need to release almost 3 times more than the downstream demand, and this is to be expected because channel storage has to change to allow higher flows. You can notice the river reach 16 has already higher flows than necessary of 68 in the previous day and 85 in the day after. So there's some water that has to be sacrificed for this maintenance of flow during one day, which equals 100 cubic meters per second. But this is the result of proper inclusion of river routing in the model. This entire project, it is in the WEB.BM user manual, but you can also download it from this link and use the restore function to restore it in your account and to test it. Let us assume that you opened a brand new account as the one you can see here. So there are no data in the account, and you want to upload the Red Deer River Basin project to test the hydrological routing. Simply open a new tab and copy the link to the database repository. Click on it, and once you're in the repository, you will see 2 tabs here. One is for the Bargy Reservoir test. The other one that is opened is for the Red Deer River Basin test. There is a download button. Click on it and click on the download. This will download the entire project into your downloads directory. You now go back to the application, the WEB.BM application, and click on the restore button. Select this option. Although this is temporary, it will be removed in future releases of the WEB.BM. And go to your downloads directory to select the file that we just downloaded. The file is called Red Deer River 2 Hydrologic Routing Tests.zip. It's a zip file. Click on it, click on the open, And now click on the upload button. So the project has been restored. Now you have to run this project because the results have not been restored, only the input data have been restored. And if you click on the scenario button, you will see that there are two scenarios here. So we'll have to run each of them. Let's go to the solver button. We'll select the project, and then we'll select, first we will run the low flow test scenario. Click on the calculate button. The solution was now downloaded, but what we can do in order to take a quick look at the solution by using the tools available in the model is you can click on the project and then click on the map. And in this particular case, you can see the schematic. Before we discuss the solution, let's quickly look at some of the input data. If you right click on this channel and click on the edit button, the channel will open in the channel list in data maintenance. The interesting button to click on here is the travel time button. And here you will see the flow versus travel time table. If we roll down a little bit, we can see that 20 cubic meters per second will approximately require 37 hours of travel time along this reach. While if we increase the flow to 100 cubic meters per second, we are down to around 19 hours of travel time. This is important to know because these travel times automatically adjust the routing coefficients. There is one more place where you specify that a particular channel will be ran using the travel time, and that is when you go to the edit form for the entire channel. You will see that this routing option use checkbox has been selected. And this is important because you may have some channels with the routing table which you do not want to route in a particular scenario, and all it takes in that case is to uncheck that box. There are other channels here which do not require any routing. They have no data in the flow versus travel time table. And also if you look at their channel form, you will see that routing obviously hasn't been selected. Now that we've seen a little bit of input, which makes this run different from other runs, one more thing to notice here is the time step. The time step for reading data from the database is daily, and also if you look at the scenario is calculated also based on a daily time step. Let's take a quick look at the results. We can use the chart option here, and if you set up the project, and the low flow test obviously was the only one that we ran so far. We can now pick a few channels to look at. We don't need to look at the ideal target for the channel because we don't really have an ideal target. This is a natural flow channel. At this point, we'll add this channel. We will add one downstream of it. We'll add another one downstream of it, which is channel number 50. And now when we click on refresh chart, we're going to see the graph, which is very similar to the one shown in the manual. Channel 30 has a combined release from the reservoir and inflow from the tributary. The peak is 306 cubic meters per second. You will see how this peak drops down as we go reach by reach. We don't have the final outflow from this channel 50 because one thing to understand here that's very important. In the map, every channel has its upstream and downstream end of the reach, and the flow at the upstream end is not going to be the same as the flow on the downstream end when we use the routing, of course. So by a convention, the plotting program shows the inflow into a river reach. It doesn't show the outflow. So we don't really see the outflow from this river reach, which should be exactly 116 cubic meters per second on the 6th of May. It would be good if we could see the outflow from the most downstream channel here. How do we do this? Well, we need to go back to data maintenance. We need to insert one more node in the system. It'll be a node of type junction. If you look at the map again, what we want to do is we want to insert one node which will split this channel into two channels such that one additional channel will have no routing. So we'll be able to see both inflow and outflow from this channel. Going back to data maintenance, we're going to introduce one more junction node. Let's call it RD9, for example. We're going to go to the channels, and we're going to introduce one additional channel. We'll call it RD70. This will also be a river reach. It will have, as its upstream node, it will have RD9. As its downstream node, it will have RD8. And we'll have to save the changes here. Also, the existing channel RD50, which used to flow to RD8, will now flow first to RD9. So now we have created a channel in between which will run on a steady state basis. And all we need to do is we need to add this channel to one of the policy groups in the scenario. Go back to the low flow test scenario, the policy group, channel policy groups. First, we need to actually include this channel and this node into the project. So there's node 9 that needs to be included in the project, and a new channel RD70 that needs to be included in the project. Now, go back to the scenario and click on the channel policy groups. We are going to add this channel to this policy. This is a policy that doesn't have any zones other than the ideal zone. And this will also require that we click on channel zones and specify zones for this channel. We have zones for all channels specified as going from Julian day 1, and we can simply do the same thing for this channel. So let's just click on the export button here, open this form quickly. Then we can use the same information that we're using for other channels for this channel. So once we click on RD70, you will see nothing here. Then we can click on paste from the clipboard, click on save all, and that should take care of this channel, same way as it does for all other channels in this group. So we should now be able to go back to the solver, run the solution, again return to the reporting tools, click on chart. You now see that there is another channel, channel 70 at the end of the list here. So we can click on channel 30, add it to the list, channel 40, add it to the list, channel 50, add it to the list, and channel 70, and add it to the list. And click on refresh chart, and now you're getting the plot that you see in the manual with this channel 70 showing exactly 116 cubic meters per second as flow on the 6th of May. This is probably not the best way to look at the chart because we are still dealing with average flows per day. So how about if we go back to setup and show these, instead of linear, show them as histogram type flows, and then redraw. What we wanted is the flow of 116 cubic meters per second at the end of reach RD70, which is the reach that supplies both water demand to the diversion and flow to the most downstream river reach. The most downstream river reach requires 16 cubic meters per second minimum maintenance flow. The diversion requires 100. This could have been solved using trial and error. On such a simple system, it would require a lot of effort, while by using optimization and built-in convergence process, we can solve much more complex and complicated systems than this. Going back now to the other scenario, since we have two scenarios and we've changed the project now, we changed the connectivity between the components. We still have to do the same thing we've done for the previous scenario, and that is we have to include channel 70 in this policy group, and we also need to go to the channel zones option and make sure that this channel also has its zone, same as the other channels. Click on the save button, because this was pasted because we already copied it from the spreadsheet before. And now we can go ahead and run this routing test. This is a run now for 40 days, requiring 9 iterations. So this is multiple time step optimization over 40 time step, which is called 9 times. So it does take a little longer, but again, it's not too long. As you will see, the solution comes within 20 seconds or less. Let's take a look at the output. Reporting tools, chart. This time you are going to see 2 scenarios. So we're going to have the low flow test, the first one we looked at, and this is going to be the second scenario we're at. You have to carefully select which scenario you're looking at because the solutions are different. We can again select to look at these 3 channels. Here the interesting thing is going to be looking at how the channel handled a 100-year flood, or how the system handled a 100-year flood. What you see here are the combined releases from the reservoir and from the tributary. So when the tributary outflow peaks, the reservoir release is reduced such that the routed flow through the city remains at 950 cubic meters per second, which is the target we want to maintain to minimize the flood damage. And again, this could have been achieved using iterative runs, but you can see the combination of hydrologic routing, reservoir routing as well, because there is an outflow versus elevation curve here used for the reservoir, or a spillway curve. And both routing of reservoirs and channels was utilized here to obtain the solution which meets our goal. And the goal in this particular run is to minimize the flood damage by keeping the flow within 950 cubic meters per second as it flows through the city. Historically, this flow reached 1,260 in 2013 June flood. One final analysis for this simulation run is to look at the reservoir levels and to find an interesting plot for this flooding scenario where the maximum elevation that was allowed was reached. It was 949.5, and the elevation stayed there for 1 day. We can also plot this together with the channel flowing through the city. We can add channel together with the reservoir plot and use the second axis for this plot. And this will be interesting to look at, because at this point you can see that the maximum channel flow of 950 cubic meters per second, and that's on the second axis here, and the maximum storage level were met and lasted only for 1 day. The channel remained at the maximum for 2 more days. It took a little more than 10 days for this reservoir to come to a proper drawdown to achieve this operation. And the reason for this is a small outflow capacity of the bottom outlet, which requires time to draw the reservoir down. This is typically what we would be looking at when analyzing the results of flood routing. Keep in mind, all these constraints, reservoir routing, channel routing, were included in the optimization. This finishes this tutorial. I'd like to thank you for your attention.